What do you think lasts longer? The Egyptian pyramids or a plastic bag? Most people would say the pyramids. After all, they've stood for over 4,000 years. But here's the thing. We don't actually know how long a plastic bag lasts. Because the first one ever made? It still exists, somewhere. In fact, every single piece of plastic ever created is still on Earth right now. Every disposable fork, every bottle cap, every wrapper from 1950, all of it, still here. We invented a material that never dies. This is the story of plastic. In the early 1900s, humanity had a problem. We were running out of elephant tusks. Ivory was everywhere. Piano keys, billiard balls, combs, buttons, knife handles, decorative carvings. The demand was so high that African elephants were being slaughtered by the tens of thousands every year. At the current rate, they'd be extinct within decades. The world needed a replacement. Something that could be molded, shaped, mass-produced. Something synthetic. A Belgian chemist named Leo Baekeland was about to give them exactly that. But what he created would go far beyond replacing ivory. It would reshape civilization itself. Within 50 years, plastic would be in every home, every car, every product. It would enable modern medicine, revolutionize packaging, make products cheaper and more accessible than ever before. It would be called a miracle material, the foundation of the modern world. But there was something no one understood about this miracle material. It was immortal. And that immortality would create the largest waste crisis in human history. From the depths of the ocean to the peak of Mount Everest, from the Arctic to the human bloodstream, plastic is everywhere. We've created over 9 billion tons of it, and 91% has never been recycled. Let's trace this thread. To understand plastic, you need to know what it actually is. The word comes from the Greek plastikos, meaning capable of being shaped or molded. And technically, plastic isn't one thing. It's a category, a polymer. Long chains of molecules bonded together in repeating patterns. Think of it like a chain-link fence, except at the molecular level. Each link connects to the next, creating strength through repetition. Nature makes polymers too. Silk is a protein polymer. Amber is fossilized tree resin. Natural rubber comes from tree sap. But those are natural polymers. They break down, they decompose, they return to the earth. What changed everything was synthetic polymers. Polymers made by humans, made from oil. The story begins in 1869. An American inventor named John Wesley Hyatt was trying to win a $10,000 prize. That's about $230,000 today. A billiard ball company in Albany, New York, called Phelan and Calendar, needed an ivory substitute. They were desperate. Elephant populations were collapsing. Ivory prices were skyrocketing. They needed something else. Hyatt had an idea. He mixed cotton fiber with nitric acid and camphor, creating a hard, moldable substance. The process involved dissolving gun cotton in a solution of camphor and alcohol, then heating it under pressure. The result was called celluloid, the first synthetic plastic. It worked, sort of. Celluloid could be molded into shape. It could be dyed different colors. It was cheaper than ivory. But celluloid billiard balls had one significant problem. They occasionally exploded on impact. The nitric acid made them unstable. One Colorado saloon owner wrote to the company complaining that every time the balls collided with a sharp crack, every man in the room pulled his gun. Not ideal. But celluloid found other uses. George Eastman used it as film stock for early cinema and photography. It revolutionized the movie industry. Detachable shirt collars, toys, combs, and jewelry were all made from celluloid. It was a start, a proof of concept. But it was unstable, highly flammable, and limited in its applications. The real breakthrough came in 1907. Leo Baekeland was born in 1863 in Ghent, Belgium, to a cobbler father and a housemaid mother, working-class origins. But brilliant from a young age, he earned his doctorate in chemistry at the University of Ghent at just 21. He moved to America in 1889 with $600 to his name and a fierce ambition. Within a decade, he'd invented Velox photographic paper, which could be developed under artificial light rather than sunlight. Revolutionary for the photography industry. He sold it to George Eastman of Kodak in 1899 for $1 million. That's about $32 million today. He was 43 and financially independent. He could have retired. Instead, he went back to his lab. Baekeland was obsessed with creating a synthetic shellac. Natural shellac came from the secretions of elac beetles in India and Thailand. It took 15,000 beetles to produce 1 pound of shellac. It was expensive, limited in supply, and the quality varied wildly. Industry needed something better, something consistent, something he could make in unlimited quantities. In his home laboratory in Yonkers, New York, Baekeland experimented with phenol and formaldehyde. These chemicals, when heated under pressure, created a resin. But it was brittle, unpredictable, and often just turned into an unusable goo. Other chemists had tried this combination before. Adolf von Baeyer had experimented with it as early as 1872. They'd all given up. The reaction seemed impossible to control. Baekeland didn't give up. He approached the problem systematically, like the trained scientist he was. He modified the process, controlled the temperature precisely, adjusted the pressure in stages, experimented with different ratios of chemicals. He built a specialized piece of equipment he called the Baekelizer, a pressure cooker that could reach 300 degrees Fahrenheit and apply controlled pressure. For months, he filled notebooks with failed experiments, too brittle, too soft, wrong color, wrong consistency. On July 14, 1907, he got it right. The result was a hard, moldable, heat-resistant material unlike anything that existed. It could be dyed any color. It could be shaped into any form. It didn't conduct electricity, making it perfect for electrical insulators. It didn't burn easily. And once hardened through a chemical process called cross-linking, it stayed that way forever. You couldn't melt it down again. You couldn't reshape it. It was permanent. He called it Bakelite, the first true thermosetting plastic. The world would never be the same. Bakelite was an immediate success. By 1910, Baekeland had founded the General Bakelite Company. He presented his invention at a meeting of the American Chemical Society in February 1909. The reaction was electric. Here was a material that could replace expensive natural materials across dozens of industries. The applications seemed endless. Telephones. By 1920, nearly every telephone in America had a Bakelite handset. Radios. The dark brown or black Bakelite radios became icons of the Art Deco era. Electrical insulators, switches, and outlets. Jewelry. Automotive parts like distributor caps and gear knobs. If you wanted something mass-produced, durable, and electrically non-conductive, Bakelite could do it. Baekeland became wealthy beyond measure. He appeared on the cover of Time magazine in 1924. The magazine called him the father of the plastics industry. But Bakelite had limitations. It was brittle if struck hard enough. It only came in dark colors because of the phenol's natural brown tint, and it was relatively expensive to manufacture, requiring high pressure and precise temperature control. The real revolution was still to come. In the 1920s and 30s, chemists around the world began cracking the code of polymers, understanding the fundamental chemistry, Each breakthrough created a new type of plastic with different properties. 1926. Waldo Seaman at B.F. Goodrich invented polyvinyl chloride, PVC, while trying to develop an adhesive. 1933. Eric Fawcett and Reginald Gibson at Imperial Chemical Industries discovered polyethylene accidentally when their high-pressure equipment leaked and contaminated their experiment with oxygen. The contamination triggered an unexpected polymerization. 1935. Wallace Carruthers at DuPont created nylon after years of research into polymer chemistry. It was immediately used for toothbrush bristles. Then, stockings. Nylon stockings became a sensation. Women lined up in the thousands to buy them. Each new plastic had different properties. Some were flexible like polyethylene. Some were rigid like polystyrene. Some were transparent like acrylic. Some could withstand extreme heat like Teflon, invented in 1938. But the real explosion came after World War II. During the war, plastic production in the United States increased by 300%. Natural materials were rationed or inaccessible. Rubber supplies from Southeast Asia were cut off by Japanese control. Silk was needed for parachutes. Metal was needed for weapons. Plastic filled the gaps. It was used for everything. Parachutes made from nylon, helmet liners from phenolic resin, aircraft components from plexiglass, radar insulation from polyethylene. Even blood plasma was stored in plastic bags instead of glass bottles, saving countless lives by making battlefield transfusions practical. The government invested heavily. Chemical companies like DuPont, Dow, and Union Carbide expanded their factories, subsidized by military contracts. When the war ended in 1945, all that production capacity didn't go away. Billions of dollars in infrastructure, thousands of chemists and engineers, entire factories tooled for mass production. It just shifted targets, from military to consumer. Chemical companies had invested massive amounts in plastic production. They needed new markets, and post-war America was the perfect customer. The economy was booming. The GI Bill put money in veterans' pockets. Suburbs were expanding. Families were moving into new houses that needed to be furnished. Everyone wanted modern, convenient products. The plastics industry launched one of the most successful marketing campaigns in history. The message was simple. Plastic meant progress. Plastic meant modernity. Plastic meant freedom from the drudgery of traditional materials. Why wash dishes when you could throw them away? Why repair things when you could replace them cheaply? Why deal with heavy glass when you could have lightweight plastic? The Society of the Plastics Industry held an annual trade show that became a showcase for the future. Plastic houses, plastic furniture, plastic clothing. Tupperware parties became a cultural phenomenon, selling plastic food storage containers to suburban housewives. In 1955, Life magazine published an article titled "Throwaway Living." It featured a photograph of a smiling family tossing plastic plates, cups, and utensils into the air. 40 items in total. The caption celebrated how disposable products could cut down on household chores by 40 hours a year. What the article didn't mention, where all those thrown-away products would go. The question never even came up. Disposal wasn't part of the conversation. By 1960, the United States was producing 6 million tons of plastic per year. By 1970, 24 million tons. By 1980, 50 million tons. The growth was exponential. The plastic boom had arrived. Here's what made plastic so revolutionary. It could do almost anything. Need to package food? Polyethylene wrap kept it fresh. Need to store liquids? PET bottles were lightweight and unbreakable. Need to insulate wires? PVC coating was perfect. Need to make furniture? Polypropylene was durable and cheap. And it was cheap. incredibly cheap. Plastic was made from the byproducts of oil refining, literally the waste products from making gasoline, ethylene, propylene, benzene. These were gases and liquids that oil refineries had to do something with. The chemical companies had figured out how to turn refinery waste into valuable products. It was almost too good to be true. But here's the thing about plastic. The same property that made it valuable also made it dangerous. It doesn't break down. Natural materials decompose. Wood rots, consumed by bacteria and fungi. Paper dissolves in water and decomposes within weeks. Metal rusts through oxidation. Even glass will eventually break down over thousands of years. But plastic? Plastic is made of carbon-carbon bonds in long polymer chains that are essentially indestructible under normal environmental conditions. Bacteria haven't evolved enzymes to break those bonds. UV light can make plastic brittle, breaking it into smaller pieces, but it doesn't destroy the molecules. Those polymer chains don't break apart. They just sit there. Forever. In the 1950s, this seemed like a feature, not a bug. Durability was good. Permanence was good. Products that lasted were valuable. But no one was thinking about what happens when you make billions of tons of permanent material and then throw it away. By the 1980s, the signs were becoming impossible to ignore. Beaches covered in plastic debris. Coastal cleanups were pulling tons of plastic from shorelines. Seabirds were dying with stomachs full of bottle caps and plastic fragments, starving to death because they felt full but had no nutrition. Sea turtles were eating plastic bags, mistaking them for jellyfish, their primary food source. The bags would block their digestive systems. But the problem was still seen as localized. An aesthetic issue. Littering. The solution promoted by the plastics industry? Anti-littering campaigns, crying Indian public service announcements, individual responsibility, don't litter. Problem solved. Except it wasn't solved. Then in 1997, a sailor and oceanographer named Charles Moore was crossing the North Pacific. He'd just competed in the Transpac sailing race from Los Angeles to Hawaii. On his return journey, he decided to take a shortcut through the North Pacific Gyre, a massive, slow-rotating ocean current that commercial ships usually avoided because it was a dead zone for wind. What he saw changed everything. For days, his boat moved through a vast expanse of floating garbage, plastic bottles, fishing nets, fragments of unidentifiable debris, toothbrushes, cigarette lighters, every kind of plastic product imaginable. It stretched as far as he could see in every direction. Day after day. Quote, "There were shampoo caps and soap bottles and plastic bags and fishing floats as far as I could see. Here I was in the middle of the ocean, and there was nowhere I could go to avoid the plastic." End quote. Moore had discovered the Great Pacific Garbage Patch. He returned to California and founded the Algalita Marine Research Foundation to study the problem. The media coverage was explosive. The Great Pacific Garbage Patch became shorthand for ocean pollution. Early reports described it as an island of trash twice the size of Texas. You could walk on it. That wasn't quite accurate. Much of the plastic had broken down into tiny pieces. Microplastics. Fragments smaller than 5 millimeters. These particles didn't form a solid floating island you could see from space. Instead, they created what scientists called a plastic soup, suspended throughout the water column. In some areas, there were more plastic particles than plankton, and the North Pacific wasn't unique. Scientists identified 5 major garbage patches in the world's oceans: the North and South Pacific, the North and South Atlantic, the Indian Ocean, all formed by converging currents that trapped plastic debris in slow-rotating gyres. Scientists began studying the scale of the problem. What they found was staggering. By the early 2000s, humanity was producing over 200 million tons of plastic per year. Of that, approximately 8 million tons were ending up in the ocean annually, every single year. That's the equivalent of dumping one garbage truck full of plastic into the ocean every minute. But the ocean was just the visible part of the problem. Plastic was everywhere. Landfills were filling with it faster than new ones could be opened. Incinerators were burning it, releasing toxic chemicals like dioxins into the atmosphere. And it was breaking down into smaller and smaller pieces, not disappearing, not decomposing, just fragmenting into pieces too small to see. Microplastics were found in Arctic ice cores drilled from glaciers that had been frozen for decades. In the Mariana Trench, the deepest point in the ocean, over 10,000 meters down. On the summit of Mount Everest, in rainwater, in the air we breathe, in the food we eat. Then scientists found them in human bodies. A 2017 study found microplastics in table salt from countries around the world. A 2018 study found them in human stool samples. Every participant tested positive. A 2022 study found microplastic particles in human blood samples. 80% of people tested had detectable levels. The most disturbing finding came in 2020. Microplastics were discovered in human placentas. The material we created to wrap our food was now crossing the placental barrier. A 2019 study by the University of Newcastle calculated that the average person ingests approximately 5 grams of microplastic per week, the equivalent of a credit card. Every week. 52 credit cards per year. The material we created to last forever was now inside us, in our organs, in our blood. We don't yet know what this means for human health. The research is ongoing, but it's impossible to avoid. Meanwhile, production kept increasing. By 2019, global plastic production reached 368 million tons. The plastics industry had plans to double production by 2040. New plastic plants were being built. New markets were opening in developing countries. The growth trajectory showed no signs of slowing. And here's the brutal truth. Recycling wasn't solving the problem. The recycling symbol on plastic products, those 3 arrows in a triangle, created the illusion that plastic was circular. Use it, recycle it, use it again. A closed loop, sustainable. But the reality was completely different. Of all the plastic ever made since 1950, only 9% has been recycled. 12% has been incinerated. The other 79%? Still here. In landfills, in oceans, in the environment, slowly breaking down into smaller and smaller pieces. Why such a low recycling rate? Because plastic recycling is technically difficult and economically unviable for most plastics. There are 7 main types of plastic, each with different chemical properties. PT, HDPE, PVC, LDPE, PP, PS, and a catch-all category for everything else. Each needs different recycling processes. You can't just melt them all together. Contamination is a huge problem. A single PVC bottle in a batch of PET ruins the entire batch. Food residue makes recycling difficult. Most recycling facilities can only handle types 1 and 2. Everything else goes to the landfill, and even when plastic is recycled, it's downcycled. A plastic bottle doesn't become another plastic bottle. It becomes a park bench or carpet fibers, products that themselves can't be recycled. It delays disposal, but doesn't prevent it. The economics don't work either. Virgin plastic made from oil is cheaper than recycled plastic. When oil prices are low, there's no market for recycled material. It's cheaper to make new plastic than to recycle old plastic. The plastics industry knew this for decades. Internal documents from the 1970s and 80s, revealed by investigative journalists, show that companies understood recycling would never work at scale. But they promoted it anyway. They funded recycling campaigns. They put recycling symbols on products. They created public service announcements. Why? Because it shifted responsibility to consumers. It made plastic pollution seem like a personal failing rather than a systemic problem. As long as people believed recycling was the solution, they'd keep buying plastic products without guilt. In 2022, researchers at the University of California, Santa Barbara calculated that humans have created 8.3 billion tons of plastic since 1950. Of that, 6.3 billion tons had become waste, most of it in just the last 20 years, and every single bit of it still exists somewhere on this planet. So what do we learn from this? First, there's no such thing as a way. When we throw something away, it doesn't disappear. It goes somewhere. With materials that decompose, that's manageable. The Earth has systems for breaking down organic matter. But with materials that last essentially forever, it becomes a crisis. We've created more plastic in the last decade than in the entire 20th century, and all of it is still here. Second, convenience has costs that aren't immediately visible. Plastic gave us unprecedented convenience, disposable everything, lightweight packaging, cheap products. But we're now paying the price with an environment saturated in permanent waste. The convenience was front-loaded. The costs are long-term and distributed. Third, individual solutions don't fix systemic problems. Recycling your bottles and using reusable bags helps. It's better than not doing it. But they're drops in an ocean of industrial production. Literally. The problem was created by design choices and economic incentives at the corporate and governmental level. It requires system-level solutions. Some countries are taking action. In 2022, the United Nations began negotiations on a global plastics treaty to regulate production and disposal. Several nations have banned single-use plastics. Rwanda has one of the strictest plastic bag bans in the world. The European Union banned single-use plastic items like straws and cutlery in 2021. Companies are investing in alternatives. Biodegradable polymers made from plant materials, mushroom-based packaging, chemical recycling technologies that can break plastic back down to its molecular components. But here's the reality. Even if we stopped making plastic today, we'd still be dealing with the 8 billion tons we've already created for generations, centuries, millennia. The plastic bottle you used this morning will outlive you. It'll outlive your children. It'll outlive civilizations. Archaeologists 1,000 years from now will dig up our landfills and find perfectly preserved plastic artifacts. Plastic was humanity's attempt to transcend natural limits, to create materials that never wore out. That could be molded into anything we could imagine. That made everything cheaper and easier. We succeeded beyond our wildest dreams. We created truly immortal materials. But immortality, it turns out, has a price. And that price is permanence, eternal persistence, a material that never leaves. The plastic we made in the 1950s is still here, somewhere in a landfill or broken down into microplastics in the ocean. The plastic we make today will still be here in 500 years, in 1,000 years. Long after we're gone, long after our buildings have crumbled, our plastic will remain. The question isn't whether we can live with plastic. We already do. It's in everything. Your clothes, your phone, your car, the device you're watching this on. Modern life without plastic is nearly impossible. The question is, can we live with immortal waste? Can we create systems that manage materials that never die? Can we design products that don't become pollution? Can we build an economy that doesn't rely on throwing away things that last forever? That's something we're still figuring out. And we're running out of time. Anyway, that's it from me. Feel free to discuss your thoughts below. You've been watching Threads of Civilization. Cheers, guys. Have a good one.